Welcome everybody to the distribution webinar of Taiwan Semiconductor here, our update on the products recently released for Q1, this first quarter. As usual, first a few housekeeping rules here. At the end, there will be a Q&A section here, so you can type in your questions here and we'll answer them at the end of the webinar. So that's one option you have. Of course, you can contact your regular sales contact also for these questions. The webinar is recorded, so that means you can actually give a copy of this webinar or listen to it again with your colleagues here if you feel like it, or you can forward it to colleagues if you want to. We will probably use also not just a complete recording, but we'll make a separate recording of the 600 volt planar diodes, which is a shorter webinar, and also we'll make a separate recording for our YouTube channel, also of the MOSFET positioning webinar here, part of the thing here. So you don't have to listen to it in 50 minutes if you don't want to, or if your colleagues are only interested in one part of the presentation, they can listen to just the shorter video here. So as we mentioned already, as we are going to recording it, and we have several recordings here, we're obviously going to use two main subjects here today. You can be regularly updated by looking at our component engineer newsletter for new products here, but we're going to go a little bit more in detail to the two major product introductions we've done in the last couple of months, or we're presently doing at the moment here. The 600 volt planar diode here is one major product introduction here, and we're also releasing automotive MOSFETs at the moment here on a weekly basis. As you can hear, sometimes there will be a short stop in the webinar because my throat is not 100% cooperative today, so I occasionally will have to stop for a sip of water. But we will get through the webinar here. So this is the agenda, and when it comes to MOSFETs here, we're not going to talk to you about our product portfolio with 40 and 60 volts coming up, also with automotive releases. We're going to also talk a little bit more about the supply chain, technology, and especially about product positioning. How do we compare with competitors? What are we actually aiming at with our new products here? Which market segments are we addressing here? And we'll also talk about support tools we have actually to support you doing the designing for our products. So let's go to 600 volt planar diodes. So we're going to talk about a product portfolio where you can compare them, the planar diodes, with GBP diodes here. We're going to look at applications, and also here again on the product positioning, where actually can you use these planar diodes here. And we're going to also look at power factor correction. PFC is the abbreviation, the PFC bypass diodes for maybe another application or datasheet update we've done here. So let's go on the product portfolio here. As you can see, we have released around 20 new products here. As you can see, they're all very fast. The TRR here is 25 nanoseconds here, so they're all very fast diodes. They come in the popular packages SMA, SMP, and SMC here, and they come in various die sizes. We can use the die in several different packages here. And obviously, as you know by now, in an SMC package, we have 3 to 8 amps here. You cannot get 8 amps out of an SMC package here, but the 8 amp diode will give you an advantage to reduce efficiency due to the lower VF at the same current rating, versus a smaller die here. So we have the major packages here. We're also introducing them in the smaller SOD123W. So we have the major packages here covered here with our new 600 volt planar diodes. These diodes are going to become the diode of choice for Taiwan Semiconductor for 600 volt applications. Let me show you why. The next slide, we're going to compare the planar diodes versus the GBP diode. The GBP stands for glass passivated pellet and is the glass passivation technology, which is most commonly used in the Taiwan Semiconductor diodes here. And most of our older diodes are produced using this technology here. So as you can tell, we have a lot of diodes here, but we're going to compare 2 amp diodes in SMP. So on the left-hand side, you can see here the planar diode here, the PU2B to JB, and on the right-hand side, you can see the ESJ2J here. So the first thing we're going to compare between the two of them is the red circles is the VF. you can easily see that at 2 amp room temperature, the planar diode is clearly superior over the GBP diode of 1.5 versus 1.7 here. I also plotted here the VF curves so that you can compare that. This is not just a text specification, but actually the real performance here. And if you look at the GBP diode at 600 volt and you look at the 25 amp curve of the planar diode, you'll see that the 200 millivolt advantage of the planar die is nearly consistent over the entire current range and temperature range. What we're seeing here is, of course, the purple line is that not only is the VF better, but you can see also that the TRR is better. 25 nanoseconds versus 35 nanoseconds for the GBP version. I'm going to talk a little bit more about TRR later on. The one thing I didn't circle here, but I would like to point out to you, is that the leakage current here is 2 microamps, is better than 10 microamps. Not so much difference, you would say. But the advantage becomes clearly outspoken on the high temperature here at 125 degrees C. You see the 7 microamp here versus the 350 microamp maximum spec here. So that's a clear advantage here. What I would like to point out to you is that the planar diodes are better characterized. What I mean with that, in the datasheet, we have the reverse recovery current and the reverse recovery charge here, highlighted in green here. Why is this important? If you look at the TRR here and the TRR definition, what you can see is that the definitions here are determined by a test machine. We make millions and millions of these diodes, and we have to do an outgoing test on them. So that's what these tests does, and that's what these test conditions are for this test machine here. You can actually fairly say that these test conditions are very far away from how a designer may use the diode here. So this information may not be so relevant for the designer, although the comparison between 25 and 35 nanosecond is. So what is important, or what is a real application condition for a designer, would be you take the maximum current here and you turn it off at 200 amp per microseconds, or you can even do it faster with an IGBT. And then, of course, you get a much higher QRR and reverse recovery current here, because they are determined by the DIDT here. And of course, the TRR varies also quite a bit with this application here. So these are applications which are closer to what the customer actually needs or actually uses it for. So this characterization helps the designer choose the right diode or get a feeling about how competitive the technology is in the real life. If you're no longer familiar with some of these abbreviations, reverse recovery current and reverse recovery charge, may I suggest that you read again application note AN1006 on our web here, power diode parameters here. So normally we talk always about the TRR, but the most important parameters determining the loss in the diode are not the TRR, are actually the storage charge, the QRR, and the peak reverse recovery current here. This one actually here gets added to the switching element, to the MOSFET here. So this you have to add to the normal losses in the MOSFET here. And this gives you an idea of the total losses in the device here. What you see is that these parameters are dependent on the DIDT here, very much here. So if you switch faster, and a lot of people like to use a higher DIDT, so in IGBT, so they can get lower losses. What happens is the line comes like this, and the peak current goes lower, and the total storage charge also becomes higher. So this is very dependent on DIDT. And the other thing that is important here to know is that the QRR and also the reverse recovery current is actually dependent on the temperature. It has a positive temperature coefficient here. What you also see here is the voltage over the diode here, where the diode actually here starts blocking at this stage. So what you need to understand is that because of the reverse recovery time and the losses here, there is not only a loss in the diode here, but there's also a loss in the switching element, which are so both absorb a loss because of this QRR. So let's go to the summary then here. So planar diodes have improved storage charge and TRR. They have improved leakage current, and they have an improved VF versus TRR performance. Let me stop a little bit at that line because I need to explain that here. If you want to improve the TRR, what you do usually is add more platinum as a material here, which then increases the VF. So there is no perfect diode. By making the diode faster, usually you make the VF worse because you add platinum here. So what you can do is compare apples to apples. Let's say the TRR is 25 or 35 nanoseconds. You have to compare that TRR, or at that TRR, you have to compare both VFs. In that case, usually the planar version is better and has an advantage here. So it's a major improvement over the old products available, and I would say it is the diode of choice for future new designs from our perspective here. So that's why we are excited to introduce these 600-volt planar diodes and expand the product portfolio in this area here, because that is going to be an important part of our product portfolio for going on in the future. Now the question is, how do you choose a fast diode here? And you could say also the planar diode is the diode of choice always. Let's distinguish a little bit here. And let's go here to a couple of very famous names in the industry: continuous conduction mode, or CCM abbreviation; critical conduction mode, or CRCM is the abbreviation; or borderline control mode, sometimes conduction mode, sometimes used also; and DCM, discontinuous conduction mode here. So we're looking at buck or boost converters. A boost converter is a step-up circuit here. A buck converter is a step-down circuit here. What happens is here, the purple line is always the current through the inductor. It's not the current through the diode, it's the current through the inductor here. And if the current through the inductor is always more than zero, we call it's continuous, because it's always on here. Whereas you can see here, the current through the inductor goes to zero and then starts up again and goes to zero again here. And here it actually meets in the middle here, and that's what we call critical conduction mode here. The diode currents are a little bit different here. So what happens here in this case here, during this phase, when the current in the inductor is going up, the MOSFET is on, and then the MOSFET gets turned off, and then all of a sudden the diode current goes from zero to the big current here, and then goes to, in this case, zero, or in this case, it stays on here. This is where two famous names in the industry come from. This is what's called hard switching and soft switching. Hard switching applications are, in this case, for the diode. When the diode is turned off, carrying current here, it's called hard switching. In that case, the QRR is the more important parameter, because there are a lot of diode losses here, or losses here because of the QRR in the diode and the switching element here. If you have switching or soft switching here, there is no actually current going through the diode when it's turned off here. So the VF becomes a little bit more important in this application. The diode just has to be fast enough here, because the diode also determines things like EMI here. So what you have here in soft switching here, you have a fast diode, but sometimes if that diode is fast enough, making it faster by reducing the QRR doesn't give you any benefits in this circuit here, and then that increases the VF, and that becomes a disadvantage here. So in soft switching, you have to get a better balance between the QRR and the VF. In hard switching, it's very easy. You always use these planar diodes here. So let's look a little bit more than in detail to our website, because what do you do actually in this case in soft switching diodes here? You look at our website here, and this is a screenshot here. What you see here, you see fast recovery, high efficient recovery, super fast recovery, and ultra fast recovery rectifiers. These are more marketing named than scientific descriptions of the device here. There is a difference between these diodes here, or the way fast diodes are made. Some of them use epitaxial material, some of them don't, and there are also maybe different diffusion techniques between some of these diodes here. But in general, the classification can also be on the somewhat random side here in this case, and that's sometimes confusing for people that design diodes. So let's take an example. You need to select a diode, 600 volt, and you're actually in discontinuous mode. So you're, let's say, doing a power factor correction in a lighting IC for 25 or 30 watt. Discontinuous mode, or DCM mode, is usually used in lower power applications here, where continuous conduction mode is used in higher power application. What you find out is you type in 600 volts on the diodes, you get 357 600 volt diodes from Taiwan Semiconductor. Also the standard ones, not just the fast recovery ones here. So of course you can ask, do I need to be automotive qualified or not? That may actually reduce the amount of parts you selected here. But then from that perspective here, you would actually go for 1 or 2 packages, maybe SMA or SMB, whatever you feel is comfortable in your application, or you use a current here, 1 or 2 amp or 4 amps or something like that. You select 1 or 2 packages, and then you export it to Excel here. And then you make a VF versus TRR comparison in your Excel suite to select the diode that is most appropriate for you. Here, in many cases, the planar diodes will come out here, but you might also find other diodes that are acceptable in soft switching here, which may, in the case of non-EPI, may have a lower cost here. In the case of EPI, I'm sure our planar diodes will be priced equivalently to the ES GPP versions here. So this makes the soft switching application or the soft switching choice of diode maybe a little bit more complex than the hard switching here. But for hard switching, it's always planar. Let's look at power factor correction or PFC here. That's where a lot of 600 volt diodes are used. What you see here is a circuit here. Let's go from the left to the right here. The picture is taken from application node 53, which is the most important or one of the most famous application nodes about active PSC from power integrations here. So we go from the left, we see here the current limiting, the fuses, the resistors here, the voltage limiting here, the MOV. You always use varistors on the mains, not TVS. And then you have the EMI filter here, which is an important part of the application here. And then you come to the bridge rectifier, is of course where we are interested here. And then in the case of power factor correction, this capacitor here is actually just there for high frequency reasons and filters out the EMI. So the main storage capacitor is after the wave shaping section here. So there are 2 diodes in this circuit. The one is the famous power factor correction diode, which can either be silicon carbide or silicon, depending on your cost efficiency trade-offs sometimes in the application here. And of course, if you use CCM, continuous conduction mode in case of silicon carbide, and then you have in the boost circuit, you also have this big inductor here. What happens actually is that this inductor here and all this circuit is actually set up here to just top off the output capacitor here with energy here each time some energy is taken off by the load here. So there is a modest current here. During startup here, of course, you get current here, maybe 100 or 200 amps or even more here. And the circuit is not really laid out for that here. So it does create with the DIDT all kinds of strange things which can lead to circuit failures here. Also, the D1, the silicon carbide diode here, silicon carbide has a positive temperature coefficient, and the die size tends to be very small here, so they don't have very good surge rating. So they can also be thermally destroyed by the surge more easily than silicon here. So what happens is, what you do is you use a bypass diode here. And so this bypass diode is used whenever the power goes up a little bit. You don't use it at 25 watts, but you start using it well over 100 watts here. But it is an important part of the circuit, and it only works here for a couple of milliseconds. That's all it does here. And after a couple of milliseconds, the normal power factor correction circuit takes over. The only important part of this bypass diode here is its surge rating. And the surge rating is usually very high, so it's actually not a small die here. So it's an important contribution to the overall ASP we can actually sell here. Regarding this bypass diode, the most common one used here is the S3 series here in SMC. That's the most common diode here in bypass applications here. And we added to our datasheet the 1 millisecond rating specifically for this application. A lot of the surges here on an empty capacitor are in the area of 300 microseconds or 500 microseconds in that area. So the 1 millisecond ratio or the 1 millisecond data in the datasheet gives the designer much more comfortable. It makes it much more comfortable choosing the S3 because it just has to not look at the 100 amp surge rating, but he has to see if to be under the 230 amp, and that actually makes his life much more easy here. So that was the most important part here for the surge rating here and the 600 volt planar diode here. Let's go to our MOSFETs, and as you know, we use the trade name PerFETs. for our new split gate technology MOSFET here. So let's update the product portfolio and look at the new automotive releases here, while we give you some more, information on product positioning and the supply chain to help you sell these MOSFETs here by yourself. So TSC is in the MOSFET business for 10 years here. I'm just always starting here, so to build the ground here. We released the first automotive MOSFETs in Q2 2020 using a standard trench process here. We have been working on a split gate technology, SGT, or shielded gate is another industry name that's used very often, for several years here, and we introduced our first industrial split gate technology MOSFET in Q2 2022 here. And that is an important milestone for us because split gate technology is quite complex to design here. We introduced our automotive version of the split gate technology MOSFETs, the first one in March. We're actually in the process of introducing them nearly on a weekly basis now, and we may have capacity, and we really actively want to grow our automotive split gate technology MOSFETs in 2023 here. Whereas with diodes here, it's easy to say, we have a product portfolio that covers 90–95% of the business, the same with TVS. So you can design everything here with our diodes here. In MOSFETs, we have 290 part names, of which 194 are active, and that includes super junction, the 600-volt ones here. So the focus of the webinar is, of course, here is to pinpoint where we are active here and help you focus your resources so you don't spend time cross-referencing hundreds of part names and that type of stuff, of which we may only have 10 or something like that. So we really want to focus you on these new parts, 40 and 60 volt MOSFETs. I'm going to go quickly over a couple of slides. There are actually more information here, but we're not going to read 100 part names here. So these are the ones we used, the first automotive MOSFETs which we introduced, which were trench technology here, and which went from 2.5 to, in this case, 40 volts to 15 and 5 to 30 milliohm on a 60 volt process here in sideway or flank packages here. So those are the ones we've got actually on the market for quite some time, and actually we're selling those and are relatively successful in those MOSFETs, and they have been quite a success. So we've entered the automotive MOSFET market already more than 2 years now, and we're moving on here now to what we call the PerFET technology. What is the difference between, this is the design here, I'm not going to go in detail to the design of a split gate technology MOSFET here, but it has two or three big advantages here. One is the improved specific on resistance, that the resistance per square millimeter. So for 7 milliohm die, things like that, you can get actually here the die size with the old ones, with the trench ones versus the split gate ones. If you use sometimes copper clips, can be between 25 and 50% smaller here. So you can get also a better RDSON in smaller packages here. So that's one of the advantages we've introduced in PerFET technology here. The other one is the switching performance here, better characterized by the figure of merit, abbreviated as FOM here, so which is the QG by the RDSON here, where you have a 40% improvement versus the previous generation. That is actually important if you are in high switching applications here. So MOSFETs can be used in many different applications. We're going for that later on here, but of course, if the faster you're switching, the more important the figure of merit comes to. And of course, linked to that are smaller input and output capacitance here. Because we have an inbuilt snubber, we have better EMC behavior here. The PerFET versus conventional behavior here is highlighted here in these curves, where in this curve, with the QGD curve here, where both the FET is conducting voltage and current here is where most of the losses are happening here. So that is lower switching losses because of this. We have a lower temperature coefficient. The RDSON of a MOSFET unfortunately has a positive RDSON. That's the same for everybody, and especially automotive people applications, when the ambient temperature goes up to 100, then the TJ becomes very high, and actually, so you'll see that the temperature coefficient is much lower here. NH is what we call the new generation, NB is the old generation trench, NH is the new generation split gate technology here. And you can see the temperature coefficient being significantly lower, which is a big advantage here at lower temperature. And of course, the process is ACQ qualified, or can be ACQ qualified here. So where do we stand here with this PerFET technology, with all these advantages? Here, what do we have? So I'm not going to read through all part names here, but these are the part names that have been actually in production for quite a while now, for more than a year, and the business on them is running fine here. So we've got quite a few orders on them here. So we have in production PDFN 5x6 here, side level flank package here, from 1.9 to 7 milliohm in both standard level and logic level with a different VGS, and the junction temperature is 175 degrees C. So those are the key parameters that we can show you to. We also have the dual version in production here, and we have the PDFN version also in production here. So those are in production for about 1 year now. One of the things here, if there's one thing we want to make you remind of this webinar, is that something we need to point out here is that when you see here everything in production here, the 1.9 here, it's a manufacturer calling something called aluminum ribbon wire bonding here. So this is this way of approaching or attaching the gate source and everything to the die here. Whereas in this case, with the copper clip here, with the ones with the larger, lower RDSON here, actually here it's the copper clip that makes the attachment between the lead frame and the die here. The difference between those is that the RDSON of this type of construction here is a 0.6 milliohm lower than this one here. So there is an advantage here to use this part here. The disadvantage is that the metallization scheme for making this product here is more complex than this one here. So you actually lose some wafer cost here. So everybody makes his or her trade-off when to introduce the copper clip package or not. And we have chosen to do it for the big die only here. On a 7 milliohm MOSFET, the difference of 0.6 milliohm is peanuts here, whereas maybe the higher metallization costs are maybe easily offsetting it here for us. At least everybody may have a different cost calculation here. That's something you need to be aware of here, because also that is, you'll see that showing up later, much later actually, also in the presentation here. So I just pointed that out here, copper clip versus the ribbon bonding here. So now we are here, and we are actually here. Follow our component engineering newsletter and our website and what your salespeople are saying here. We are now introducing MOSFETs on a nearly weekly basis here. So what you see here, sorry, I'm going to go back here, is that the copper clips for the non-automotive are coming out in April 23. So that's next month. And so we're also will have 1.2, 1.1, and 1.3 million MOSFETs here, 40 volts, starting next month here. When you come to automotive here, you'll see that is what we'll have here is that the range which we have actually introduced here is the 40 volt range here will be completely made automotive here. That is in qualification going on. We have our first parts in production here. So we've already shipping the products in volume here to customers here, and we're working on the paperwork to introduce our 1.9 to the 7 milliohm MOSFET line here in automotive versions here. And of course, for automotive, the only difference is that, you know, we'll take a little bit longer to introduce the PDFN 3x3 package here in automotive. That's only going to happen in March next year. And of course, we're also going to take a little bit longer here to introduce the copper clip in automotive here. That's also scheduled for March 2024 in 1 year's time here. But in the meantime, we will be able to promote these products for which actually in the automotive market, the business is actually fairly substantial. 60 volt, we're not going to go through our entire roadmap, but this is close enough here. So we're close enough to releasing a 60 volt roadmap here, our 60 volt roadmap here, and starting to promote here our 60 volt version here in the PDFN 5x6 package here. We start at without the aluminum ribbon bonding here. We start at 2.6 milliohm, and we're going here to 13 milliohm, and we have a 14 milliohm dual version here. And we're also introducing the products in the PDFN 3x3 package here. So our 60 volt versions here are actually on the road here, and we're going to be close to promoting these. So in the next component engineering newsletter, you'll get more information about this. but this is something here we already want to highlight to you, that we're pretty sure close to shipping 60-volt split gate technology MOSFETs in these packages here. Again, the copper clip and PDFN package are slightly delayed to that should be reading July 23 here, and not oh sorry, the automotive versions. These dates are of course correct here. The automotive versions are again same as the 40-volt versions here, with the PDFN being delayed to next year. What do we have to promote here on the 40-volt product here? So first and for all, we have on our online design resources, we obviously have the data sheet here, but we also have the SPICE model here and support in that area here. We also have an applications team that can support you with help you with specific applications here, choosing RGs or whatever problems you may experience in your circuit here. We actually have very experienced applications people in our headquarters here. And of course, we also support it now with all our products with Snap EDA here to improve layout and design questions in that area. We have two more things which I would like to briefly highlight to you here. One is application notes. One is comparing the PerFET the split gate technology here with the transition MOSFET here, which is the the previous generation. So we have extensive application note here detailing all the advantages here, which you can share with your customers here. And we're actually only introducing the package with the wettable flanks, not with standard products here. So all automotive customers know what wettable flanks are, but maybe some of your distribution customers have not heard of wettable flanks here and the advantages in optical inspection here. So that's why we have a second application note to actually also explain that, which could benefit you promoting the products here. Let's go now to the supply chain, and here we've got 2 or 3 slides here. So what we're doing here in the case, let's talk a little bit about the MOSFET cycle times here, how long it takes to manufacture a MOSFET in ideal circumstances without bottlenecks here. Sometimes you reach or you hear in the market that per mask you ask 1 mask 1 week lead time or 1 week cycle time, I should say here. In the MOSFETs, it's a little bit more complex here because this first mask where you make the trenches and dig the trenches here is actually quite complex and time consuming here. So what happens is frankly speaking here, you need more like 8 or 9 weeks to make the wafers in case of a MOSFET here. Then the next step here after the wafer fabrication here, you move on to chip probing here. Chip probing is like 1 or 2 weeks here, and BGBM stands for back grinding, backside metallization. What happens is a MOSFET has a certain wafer thickness here, and that wafer thickness is only increases the RDSON here. So you grind the wafer here, make it thinner here to improve the RDSON here. That's another step that might take 2 weeks or something like that. And then you go to the back-end assembly 2 or 3 weeks here. If you look at the MOSFETs here, we've already talked about the PerFET front end quite a bit here. It's UMC, one of the biggest foundries in the world. So when it comes actually to wafers and the amount of wafers available, we don't have such a bottleneck on it at all. So these people make millions of wafers here. Gradually, as the lithography goes down and ICs become more and more complex here and move to a smaller lithography, more and more capacity will become available in the nodes that we tend to use on MOSFETs, and that's 0.8 micron or 0.15 or somewhere in that area, 0.13 maybe in the future here. So that is for us the front end is actually well covered here. UMC is not just a foundry partner; they are also investors in our company and actually sit on the board of directors. So we do have a close link to them here. So what happens here for us here, the challenge is more on the back end here is building enough capacity for the PDFN 5x6 that actually meets automotive capabilities here, because we want to do everything. Everything we do, we want to be automotive capable here. So that is where the back end is, where we have one partner here, but where Taiwan Semiconductor is actually also investing quite a bit of money in building its own back end capacity, first for PDFN 5x6 side with wettable flanks here. So actually, so this is one slide here just to show you how serious we are here. So we are known mainly as a rectifier company, but a lot of our investments at the moment are going into MOSFETs here. And here, this is a picture of our factory backend in Taiwan, where there is an expansion plan, and already in that factory, we are actually assembling MOSFETs here. So a lot of investment from Taiwan Semiconductor is going into the MOSFET backend here. So we are committed to this market, and we are in this market for the long term. Talking about the backend here, so you know, the suggested pad layout here. Here we have all our friendly competitors here on this slide here, whether we're talking about NEXPERIA or onsemi or Infineon or ST or Vishay here. They're all a little bit different to do this wettable flank process here. That they all have a little bit difference here, but you can actually have a combined layout, which actually makes you compatible with most of these people here. When there is a will at the customer to do so, it is actually easily possible to second source these things from a mechanical perspective here. That brings us, of course, to competing with our competitors to the front end, if the back end is actually straightforward here. And now we're going to talk a little bit about the front end of MOSFETs and how we compare with our friendly competitors, and a little bit more about cross-referencing, if you can cross-reference a MOSFET at all here. So the key product positioning is actually linked to the process, to the split gate technology process we have. That determines the data sheet. The rest is just a different die size. And so that's all, everything is determined by the process. That's not just for us, but that's also for our main competitors here. It's the same thing. These processes are determined by two things. We already mentioned it. The figure of merit and the specific on resistance. The figure of merit is either RDSON multiplied by QG or QGD. That's what, you know, this is a crude parameter. This is not necessarily the most sophisticated parameter, but it's easy to do because a data sheet designer opens his data sheet and he can do this in less than a minute, compare the two things. So then he knows what he stands here. Whether that's relevant for him or not, it just assumes that, you know, that both switching losses and RDSON or conduction losses are equal. In a lot of applications, they aren't. One or the other is actually much higher than the other here. But it is, you know, what is used in the industry. The second one is the specific on resistance, which is the RDSON per square millimeter. And that actually depends on the cost. Of course, the die size, it determines the cost here in this case. But obviously, you know, also you might reduce the RDSON per square millimeter by making the process more complex here. So those are all trade-offs you need to know here. And then, of course, all these figures are linked to a specific voltage here. So 40 volts, 60 volts, and things like that. For if you go to a different voltage, these figures are completely different and things like that. That's why when you cross-reference the MOSFET here, the first thing you do is match the voltage here. You match 40 volt with 40 volts and 60 volt with 60 volts, because these key parameters for the process are completely different for different voltages here. The next thing you do is go for the package here. You might want to see, you know, obviously customers want to keep the package the same here, and then you want to match the RDSON as closely as possible with your design here. And then, of course, you want to, especially in the 40 volts we're introducing here, you want to match the logic level with logic level, or standard level with standard level, which means standard level being the VGS at 10 volts, and logic level also offering a gate capability at 4.5 volts here. The rest here actually is you can cross-reference as much as you want to here if you want to. This actually determines, because the process is unique here, this determines all your AC parameters. So there's no point in looking at the AC parameters too much here. Frankly speaking, if you match those, you get the RC parameters. You cannot really influence them that much, although we'll talk a little bit later on about high frequency switching applications more here. Good cross-referencing actually depends on your application knowledge here. So if you really want to do a good cross-reference, you better know what the application is, so you get a feeling where the losses are going to come from. Otherwise, you're actually guessing more than actually cross-referencing in this case. So let's look a little bit more at 40 volts here and where they are predominantly used here, or MOSFETs actually in general here are predominantly used in these applications here. You can turn them on and off here with the power switch, or in many cases also called the load switch here. Or, you know, this is a battery pack, but in cars, automotive, it's going to be predominantly polarity protection here for the disconnecting the battery here. So that's the number one application here. In that application, the RDSON or the specific RDSON is the key parameter for the process here. If you look at motor control here, it could be industrial applications here like power tools and things like that, but a lot of fans here. But a lot of the BLDC motor control, actually the biggest market for that for 40 volts, will be actually in cars here. What you see here, you're looking at frequencies of 16, 32, 40 kilohertz in that area, sometimes even lower here. So what you see here is the conduction losses are 80 or 90% of the total losses here. The switching losses aren't that important here, or not a major contributor to the contribution to the total losses. So again, here the specific RDSON is actually important here. Then we're moving to the right-hand side here to the high switching frequency applications here, where you have a synchronous rectification, where the rectifiers are replaced by MOSFETs here, and of course DC to DC buck converters here. And in this case, DC-DC buck converters here, they switch at, they can switch anywhere from 100 kilohertz to 4 megahertz here. But, the high frequency operation usually tend to be in at 30 volts and not so much at 40 volts here. 40 volt is used a lot in high frequency synchronous rectification applications here. But here the frequency is something typical like 100, 150 kilohertz in that area here. But actually here, in this case, the switching losses are important here. So the figure of merit becomes the key parameter here for the MOSFET performance for customers here. So now let's look at the application and the consequences for cross-referencing at 40 volts. We're looking specifically at 40 volts here. So as we talked before, you match the voltage here, the package here, and the RDSON here. So those are the key things where you start on here. When you talk about on-off switches here, and this is just general, I mean, here in what I described here, in your day-to-day life as a distributor here, this is not more 40 volts, but you see a lot of cross-referencing at 30 volts or 20 volts. Also in SOT23 and that type of stuff for these applications and load switches here. So you match the breakdown voltage, the package, and not even the RDSON in case the currents are very low here. And then you can check out a lot of things here, but then, you just, in this case, because there's the threshold voltages here, that type of stuff in battery operated applications become important here. But what you can also do is actually just try your luck here. We have a more limited product portfolio here than some of our competitors here. That's why we don't have thousands of part names here. So sometimes it will work, sometimes it won't work. I can't tell you when it will work. With these crosses, I can give you 3 reasons why it will work or 3 reasons why it won't work. In this case, the most common approach for us is to try our luck and do the cross here and see what the customer says here. That is not the case in the polarity protection in automotive here. You have to follow all the standard cross referencing rules here. If you look at here the automotive or the motor control here, where you have your load is a motor here, in this case here, you follow the cross-referencing rules and that type of stuff, but you want to make sure that you cross-reference logic level with logic level here, just to avoid any problems later on here. And the temperature coefficient of the RDSON is actually also important here. But here it's quite possible here to replace one MOSFET by the other. So your chances of being successful with cross-referencing actually are high in this case. So this is an area where you can have a good success rate cross-referencing here. In the case of the high frequency applications here, it becomes more critical here. Obviously you do the cross-referencing here and you get the AC performance, and in this case the AC performance parameters are important here. There's not much you can do about it, apart from offering the cross-reference to the customer here and do the close match as possible here. The only thing that you need to say here, that sometimes in this area here, let's say that that the switching losses are more than 50% here, sometimes at low load or something like that here. In that case, actually it's counterintuitive. Most of the time, if people see a problem with efficiency, they go to the higher RDSON and the bigger die. If your switching losses are dominant and things like that, you improve your switching losses by going to a smaller die, not to a bigger die. So that's something that is counterintuitive sometimes and it's forgotten when you promote your MOSFETs here. So our key target here in the business here. So now let's look at our how we compare with our friendly competitors here. So we already mentioned here, of course, our key competitors are maybe Infineon, especially in automotive here, but also NEXPERIA and Onsemi. Of course, we also come across ST and Vishay a lot, but let's look at some of our key competitors here. And this time I'm making this a complex slide here, and I know we're approaching the end of the presentation here, but I just want to still make sure that you are awake and follow the application. So here we put in them side by side here. And so what is the guy going to do, the designer going to do here, is going to spend 1 minute and calculate his figure of merit. So we're looking here at the a 10 volt logic level MOSFET here. You're looking at a typical RDSON, or you can do the maximum RDSON, but I'm using the typical here in this case here of 6.1 here, and you multiply that by QGD here, which is by 3 here. And here you go by Taiwan Semiconductor here, and you multiply, you find the RDSON here, the 5.6 here, and you multiply by 4.3. If you do the multiplications, you'll see that we're slightly higher, but not much higher than actually in this case OPTIMOS 5 here. So we're confident to say that, especially in applications where the automotive applications and applications also in synchronous rectification here, we are confident that we can compete with OPTIMOS 5, which is the most popular and famous process in the business here. We know Infineon also has OPTIMOS 6, which is 1 step higher up from this with a very thin die here, but the vast majority of the business out there is OPTIMOS 5, and we feel comfortable that we have an equivalent here where if we can compete with them here, that we will probably do reasonably well here. So the only thing here that I would like to point out to you is this is the last slide. I kept the last slide, complex slides, for the end. I'm sorry about that, but that's the way, just to keep your attention here, is that sometimes it is in our advantage if people do this RDSON or this figure of merit calculation here. In the beginning, when we introduce a new line, people are not so sure about the distribution and things like that. So we are very conservative in our specifications here, where our typical voltage here on the 1.9 milliohm FET here is 1.3 here, whereas in the case of Infineon, it's 1.5. It doesn't sound like much, but it's more than 10%, right? So it's an important difference here. So in the case here, in the beginning here, if you cross-reference against OPTIMOS 5, what I would suggest is to use the typical RDSON here rather than the maximum RDSON here. Some of this thing, and that's with the next slide, are also complex, are distorted by using copper clips versus aluminum ribbon bonding. And that's the next thing I'm going to talk about later on here in a slide with the NEXPERIA here. But first, let me talk a little bit about our applications lab. So we have an applications lab which is benchmarking continuously the MOSFETs here. What we're seeing here is the benchmarking results against an OPTIMOS 5 MOSFET here from Infineon here. What you see here is LLC, that refers to the topology of the power supply, refers to this stage here of the power supply, have the input here, and here what you see, it is a 480 watt power supply. The output voltage is 40 amps, so the voltage here, output voltage is 12 volts here to get here. What you see, actually, this is not a design that's easy on the MOSFET here. It actually challenges the MOSFETs quite a bit here, 40 amps here. And what you also see here, that switching frequency of 150 kilohertz is also a reasonable benchmark here. So what you can see here is that against this OPTIMOS 5 product here, you see that we have here the efficiency here is actually quite similar here. We do the efficiency here at 100% load here, but sometimes, as you know, as we are speaking at the moment, or as when you're typing your emails, you're only using your computer at a fraction of the top power capability. You're going to use the top power, the 100% load, if you're playing video games or something like that. So there is a wide spectrum here, and you have to look at all the load conditions here, because if you go to the low load condition here, the efficiency goes down because the switching performance, actually switching losses, stay more or less the same. It's the conduction losses that only go down. So that's why your efficiency goes down here. So we think also here, this actually proves that we're doing relatively well versus OPTIMOS 5 in this case. The last one we're going to compare at, because we can't compare data sheets forever, that would order the two more slides here. So the one here, that every MOSFET has a different competitive landscape here. So now what we're doing here, we're going to the 7.6 milliohm dual MOSFETs from us, and we're comparing them with an ST device here. So what you're doing here is the 7.6 milliohm. Actually, it's a relatively small die. The copper clip is actually irrelevant in the product performance, or a very small impact in the product performance. And actually also here, it is commercially of interest here. As we go to 1.9 milliohm, or those big MOSFETs here, the ratio of the die cost to the packager cost become very high here. So it's the die that is going to impact the total cost and our competitiveness here. If the package here is or rather 7.6 milliohm, even though you have two die, there's a bigger balance, or there is a better balance between the package and the die cost here. The smaller die here, the better, and those better ratios here are for TSC here. And also this component here, 7.6 milliohm component here as a dual here, is not so attractive at all for a company like Infineon or NEXPERIA to manufacture in these packages here. So every component actually has a different competitive landscape, and you'll just have to learn about these different competitive landscape as you start promoting our products here. The last slide here, because we said 50 minutes and it's already 50 minutes, but we're approaching the end here, is again one with a lot of material here. So I just wanted you to, use your brain here and calculate the figure of merit here and find the figure of merit here on this slide in a couple of seconds here. And in this case, what I'm doing here is our released 1.9 milliohm product here. So you see the 1.9 milliohm. This is one that is released, and this is the one that's coming next month. So it says preliminary here. This is the 1.3 milliohm here with the copper clip. The difference between copper clip and aluminum ribbon bonding is 0.6 milliohm. So it's actually the same die. So the same die have the same actually AC performance here, which is the QGD is the same for the both products here. So you can do the multiplications here by the QGD multiplied by the RDSON here for both products here, and you'll see that the one when we have the copper clip here is actually quite similar to the Trench 9 here from NEXPERIA, which is the latest generation. NEXPERIA also here, NEXPERIA is the easiest one to see here, which generation they use, because they actually use it in their part names. The other ones, for example, for especially for on semi, it's virtually impossible to find you have to go to they have a complex part numbering system. You can't use their generation, find out which generation they're using, but it's not so easy here. I chose NEXPERIA because it's the easiest here. So even here, we are fairly competitive here, and your performance of our products will be fairly competitive against Trench 9, and that is the latest generation of NEXPERIA. NEXPERIA still does a lot of business in the BACK 6 and BACK 5 generations here. So and those are the older generations here. So again, here we feel like, in the product range we discussed, we will probably do very well against NEXPERIA here. So let's summarize here. We're coming to the last slides. So we designed our first split gate technology process. It's in production for 1 year, and we're shipping orders against them for 1 year. We built up a reliable supply chain for MOSFETs in that period, using not just UMC here, but slowly also developing our in-house on backend and one subcom here. The split gate technology or shielded gate technology developed is competitive here. It does well. There are a few, like OPTIMOS 6 is the exception here, but you'll find that in 80 or 90% of the cases will be relatively competitive here, and the differences are irrelevant in automotive applications here. We introduced the ACQ 101 qualified split gate MOSFETs last month, or I should say March is still, we're still in March, so this month here, and we're completing the line over the next 2 or 3 months, and we actually have here a big roadmap here, which we will sometimes share with you also here. So we are investing in MOSFETs here. And so the last issue here is we are in the MOSFET business for the long term. So I think that is the message we want to give you. We are known as a rectifier business, but a lot of our investments at the moment are in MOSFETs, and we are really focused on this business to also grow it. So I think we are actually at the Q&A section here. First of all, thanks for listening here. I will now see, sometimes we have problems seeing the questions here. So please, if I miss them here, don't worry about it. I will actually, they are recorded here and I will be able to answer them either later on today or tomorrow here if somehow a question gets missed. Let's see, okay, I'm pushing the questions button. You see, sometimes I don't see it. I don't see any questions here, but sometimes they don't display here. So I will wait 1 or 2 more minutes before closing the webinar. Good. Well, I'm sorry, I don't see any questions here. Again, if I missed any, then because it had happened before, then I will actually, reply to them later on. Otherwise, thank you very much for your attention. Have a nice afternoon and evening. Recording will be available and can be shared with you. And success promoting not only our 600 volt planar diodes, but also our MOSFETs. Thank you very much. Bye-bye.